Hello, welcome back. This is Calculus by Dr. Oz. So today we're going to go over an exercise where we're going to find the area of a surface of revolution. Let's see what we have. We have y equals 2 radical x, and we're only considering the piece that corresponds to the interval 4 and 8. And what we're gonna do here is that we're gonna revolve that curve around x-axis, and we're gonna get a surface. And what we're interested in the surface area of the three-dimensional object. And before we get started, let me just give you the formulas that we're going to use along the way. So we have the definition of the surface area of the revolution. We have two different kinds. And the first kind, the integral is represented by dx, so everything depends on x. So this is the formula you're going to use when you have y equals f of x type representation of the curve. And the second formula is you see you have the integral depending on y, so that means x is a function of y. So if you think that you have the function written in terms of y, then that means you're going to use the second formula. So going back to what we are given in the problem, I think we have the y equals f of x representation, and for that reason, we are going to have the very first formula being used to evaluate the surface area of the revolution. Let me just give you some heads up of like how the three-dimensional object is sort of like generated by revolving the curve around the x-axis. So here we go. So I rotate, I keep rotating, and this is in fact what you get at the end. So it's a three-dimensional object, and we are only interested in the surface area of the revolution. So to see the details, please watch the rest of the video and have your graphing calculator ready. So let's get started. All right, let's look at this exercise here, right? And evaluate the definite integral that represents the area of the surface generated by revolving the curve y equals 2 radical x over the interval 4 and 8, closed interval 4 and 8, about the y equals 0, which is the other name of the x-axis. So first of all, I want you guys to graph y equals 2 radical x over the interval 4 and 8, just to convince yourself that you have this nice graph popping here. Okay, let me just move this a little bit. Okay, and what I want you to do is to sort of like mark 4 and 8, okay, because we're going to revolve this curve around the x-axis. So visually what would happen is that, you know, once you rotate that, so you're going to have a surface, and I'm going to show you in 3D how this looks, okay, and we are interested in finding the surface area of this three-dimensional shape, okay? So how does this look like in 3D? All right, so this is our curve in 3 dimension, as you see. And now what I'm going to do is I'm going to start rotating that about x-axis. Let's see what it looks like. There we go. You rotate it all the way. Here is the three-dimensional picture. And what we're interested in here is to find the area of the surface here, okay? So that's exactly what we're going to do. So there's the other side of that, obviously. So we're going to find the surface area of this picture, this three-dimensional object, in fact. All right, here is the definition of the area of a surface of revolution. We have two different formulas. In one formula is you see that y is represented as a function of x. And the second formula is you see x is represented as a function of y. In fact, x equals g of y. In the top one, y is represented by the function f of x. Okay. All we do here is that we take a piece on the curve, and we try to revolve it around, and we have a frustum, and we look at the area of the frustum, which is 2 pi r, the circumference, times the arc length. And arc length comes with this formula. If you recall from the arc length formula, this part is the arc length. and then this is the circumference of the frustum. So that's once you integrate it from A to B, then you get the surface area of the three-dimensional object when you have when you revolve y equals f of x around an axis. Okay, it could be vertical or horizontal. Okay. So, but again, what you need to look at here is how the function is defined, and based on that, you're going to use either the first formula or the second formula. All right, let's go back to the problem and see what we have. And here in this formula, we have y equals 2 radical x. In fact, this is the f of x representation of the function. So we're going to use the first formula. So let me just write the surface area by capital S. So we have 2 pi integral from 4 to 8, okay, f of x, 2 radical x times 1 plus f prime of x quantity squared dx, okay? So at this moment, go ahead and try to find f prime of x. Let me just do it right here, and I can erase that later, okay? So f of x equals 2 radical x, but I'm going to write it in the power form with the exponent form. 2 times x to the power of 1/2, and use the power rule for differentiation, which is 2 times 1/2 times x to the power of negative 1/2. Okay, and if you simplify this, this is x to the power of negative 1/2, which is x to the power of 1/2 reciprocal, right? 1 over x to the power of 1/2, but in short, it's 1 over radical x, okay? So you can go ahead and use this in this formula here. So you have 2 radical x plus, so 2 radical x times 1 plus 1 over radical x quantity squared dx. Okay, let me erase this portion real quick. Okay. All right, so why don't we simplify this? So we have integral from 4 to 8, 2 radical x, radical 1 plus 1 over x, because radical x squared is just 1 over x dx. Okay. We got to simplify this further to be able to use either u substitution or the known integration formulas. So why don't we simplify this further? 2 radical x. So instead of 1, I'm going to write x over x plus 1 over x. Okay. So this implies that you have x plus 1 over x inside. So the radical, right? And one thing that I know from algebra is that radical of a fraction is a fraction of the radicals of the top and the bottom. So here we go. 2 pi integral from 4 to 8, 2 radical x plus 1, radical x dx. All right, so all of this manipulation that we had to simplify the radical is to be able to cancel this radical x by this radical x. Okay, so that this integral turns out to be, let me just use a different color here, 2 pi integral from 4 to 8, and 2, I can pull out 2 as well, so this becomes 4 pi, okay, x plus 1, radical x plus 1 dx. Okay. All right, so I'm going to clean up the rest, and we're going to work on this definite integral because we can use a u substitution to integrate or to find the antiderivative of this function. And now, in fact, go ahead and use u equals x plus 1 type u substitution as I erase the unnecessary part of this slide. Okay? All right, so I'm going to do the integration process here and for the indefinite integral. So I'm going to call u to be x plus 1 so that du equals dx, okay? So that this integral turns out to be radical u du. In other words, u to the 1/2 du, okay? And use the power rule for integration. So this is u to the 3 halves divided by 3 halves plus c, which is in fact 3 over 2 radical x plus 1. In fact, let's just write it as like with the exponent, not radical x plus 1, but x plus 1 to the power of 3 halves plus c. Okay? So now we can use this antiderivative without c to evaluate the definite integral here. Okay? So I'm going to write 4 pi 3 over 2 x plus 1 3 halves from 4 to 8. So we're using the first fundamental theorem of calculus, right, to evaluate this integral. So let's simplify also this 4 by 2. So you have 6 pi, right? 6. Oh, I made a mistake here. I'm sorry. This should be 2/3 because you have to flip the bottom, right? So you have to flip the bottom. I'm sorry. You don't cancel anything here. Let me just rewrite this part. So you have 4 pi and 2 over 3. Okay, I'm sorry. All right, so let's just finish this up. So let's plug in the upper limit. So 9 to the power of 3 halves minus 8 pi over 3, 5 to the power of 3 halves. Okay. All right, and go ahead and use the calculator value if you want to. But I'm going to leave it as is, and then the rest is just to punch this in all the way to your calculator and get an approximated value. Okay? All right, so what we got here is the exact value. So this is the exact value. And in fact, let me just find that numerical value real quick. And here is the calculator value. So 132.53 is the surface area here that we mentioned in the beginning of the problem, right? So surface area of this three-dimensional object is 132.530. All right. And in fact, this was the three-dimensional picture here, and we got the surface area of that. All right, so this is already a long video. Thanks for watching. I'll see you in another video.